Hey, hi, this is Mr. Secoder. In this video, I'm going to discuss a problem from a SPOJ online judge platform named adjacency bits count. This is actually asked by some of our friends in this comment. He asked whether I can help him in order to solve this problem. Of course, yes. So let's solve this problem and have some fun. So first, let's see what problem states. You are given a string of n bits. That's it. The adjacent bit count of that string will be given by the x1 into x2 plus x2 into x3 and so on. This literally mean is the number of times a 1 bit is adjacent to another 1 bit. So if you consider this, I will show you. If you consider that, so here the number of adjacent bit is here, these two are adjacent and these two are adjacent, so the adjacent bit count is 2 here. These two are adjacent, the adjacent bit count is 1, so total it's 3. Total it's 3, so that's what here. Similarly here you'll get 3, and here you'll get 1, so 4. So here there is no adjacent bit count, so 0. So what this question asks us is, you need to write a program which takes an input of this n and k and return the maximum number of strings with x of n bits out of 2n possible combination of this n bits. You need to find such combinations where the adjacent bit count is k. For example, if the n was given as 5, the 5-bit string with have 6 ways of getting this adjacent bit count as 2. Here the bit count is 2, here the bit count is 2, here the bit count is 2, like that. So we need to solve this problem and return the number of such possibilities, and the number of test cases is 1000, and he said that the n won't be greater than 100, and the answer will be, even said that the result will fit in a signed 32-bit integer, so you can use unsigned integer in C++. So let's see the solution. So here I declared n and k, and moreover the way here this is a number of data set, that is test cases, and this is a test case number. You have to print the test case number and then the result here. So I have read this this test case number and this n and k here, and this all is going to execute the actual logic. So we write a recursion function, and what's the logic behind this is I'll explain the logic behind this now. So you can solve this with the recursion. If you have, let's say, n bits here, let's say these are n bits, so in the last bit so here in the current bit you can set either 0 or 1. Okay, so by setting this you can go to the previous bit and you can either set 0 or 1. Okay, so if you set 0 here and if you are setting the previous bit as 0, the count won't change because there is no these two are not adjacent set bits. So if you place 0 here and previous bit if you are setting 1, the count still doesn't change because 1 and 0 don't have any adjacent bits. Okay, so if you are 1 here and you are setting 0, similarly in this case also you have no adjacent bits right next to each other. So if you are setting the bit as 1, previous set bit as 1, then the adjacent bit is reduced, so adjacent bit is incremented by 1. So if you are at this specific position, let's say you have other bits also, so if you are at this specific bit position and you want some k set bits from here, say adjacent bit count from here, if you set the previous bit as 1, then the state will goes down into calculating from here the with these many bits. That is, if you have I bits here, or let's say if you have n bits till this position, then from here you have n minus 1 bits, and you need to find whether it's how many such possibilities exist such that with these n-1 bits you can form those combinations such that you have k-1 adjacency bit count. So the TP problem, the state was decomposed in this way. It's a sub problem. So, and if you have 0 and previous bit as 1 or 0, then you will have n-1 bits, but you need to have bits adjacent bit count as k itself, because here you are not decrementing, you have no adjacent bit count here, so you won't decrement it. So this is the logic. This is a state, and we can use memorization in order to get that. So at last, if you want to find all, so if you have n bits and either the last bit is 0 or the last bit is 1, with that you have you need to adjacent bit count of k in both the cases. So with that you call the recursion call, you call this recursion call here, get possible count, will count with n bits with k as a adjacent bit count, with 0 as a current set bit, whether the set bit is set or unset. Similarly with the set bit is set. So let's see this recursion. So I'm using memorization. So if this state occurs before, then I'm returning the answer. So let's see actual logic. If the current bit is set, so the current bit is set, the number of possible ways of getting this will be, the number of bits will be reduced as you have seen before, and the adjacent bit count will same because the previous bit is set, but now current bit you are setting as 0. Okay, in that case you won't have any adjacent bit count, but if you have previous as 1 and current also 1, then the adjacent bit count will be reduced and the recursion call will be in this way. Okay, if the set bit is if the bit is not set in the previous case, then you can simply the adjacent bit count will not be reduced because you have 0 and 1 different bits, different bit. If one bit is set, then other bit is not set, so the adjacent bit count won't be decremented here. So if this state, if you see this state before, you return this state. I'm using this max possible n and k is this 100, so I'm setting as 101, so I can use 100 as an index. So yeah, if you already if you don't solve this, then you are actually setting this right here or here. So by saving that, you're returning that, save it. If you already seen this state before, you simply return the answer. And the base case is if you reach it the end of the bits, if you complete all these bits, and if you reach it here, this is first bit, if you reach it here, then that was a base case. In that base case, you are setting the adjacent bit count. If the adjacent bit count is 0 and the bit is not set, because there exists no set bits, so how can the bit be set? So if that is not set, then you return 1. If that's not the case, you return 0. So this is a top-down approach. So you can use even the tabularization instead of memorization. So you iterate over all the possible bit and bit count and adjacent bit count, and you use the same logic as this here. If you need the current bit as 0, then you need the previous bit as 0 and the previous bit as 1. The adjacent bit count won't be reduced. If that's not the case, the adjacent bit will be reduced. The same logic as of before. You can use that. So this way you can solve this problem. So as always, like, share and subscribe to my channel. If you feel this video is interesting and this problem is interesting, you can try it out. I'll put the link in the description below, and don't forget to hit that bell icon so that you can receive the notifications. And thanks for watching. Goodbye.